Hi everyone, and welcome to our video on the isosceles triangle theorem. This is a first of a two-parter. In this part, we're going to go over how we prove the isosceles triangle theorem and exactly what it is. And in the next part, we're going to put it into practice and show what kinds of problems it's useful for. I would recommend watching this video even if you already made sense of the lessons we did together or all the stuff on Agile Mind seems to make sense. We're going to go over it in a little different way, and I think it's a pretty useful way, and it might help you remember this more in the future or see why this stuff is useful and important. But first of all, let's just jump into things, right? In this picture, you might guess, and you'd be correct, I have a bunch of isosceles triangles, right? Lots of isosceles triangles here. So I would invite you to consider now, okay, what do you notice about these isosceles triangles, right? And especially when I'm trying to remember what is an isosceles triangle. Looking at these, what is an isosceles triangle, right? So consider that. All right, so hopefully you've looked in your notebook, right? Or you've looked it up real quick, or you Googled it, or you just remembered. Isosceles triangles are things with two congruent sides, right? Triangles that have two side lengths or two sides of equal side lengths, right? So all the triangles in this picture have two sides with the same side length, right? Interesting. So what else can we tell about these triangles? So I'm going to invite you to consider that as well. Maybe pause the video and look over these questions and think about it, right? What do they have in common? What it looks to be true for all of the triangles in the picture? What do you notice about their sides? What do you notice about their angles, right? And using that, what can we predict is true for all isosceles triangles? Because I tried to make triangles here that were in a variety of ways, right? Tall and skinny, short and wide, pretty equal looking, right? So all these are meant to represent different kinds of isosceles triangles, and we'll see what seems to be true for all of them. So hopefully you've given yourself a chance. You've paused the video, right? Or if not, you've thought about it. But hopefully you've paused it, maybe even written down a list. Let's see how you stack up against me, right? So everyone should have remembered two congruent sides because we just went over that one, right? But what else can we notice about isosceles triangles that seems to be true? You might notice this is similar to something we did in the past, and we're going to be reviewing that lesson a little bit, going over how we made isosceles triangles before, right? So using that, let's examine. What I see here is that each triangle has two congruent angles. So allow me to show that real quick. I'll annotate here. All these triangles have two angles that appear to be the same as each other, the same angle measure as each other, right? Same length measurements. So they're congruent angles. I can see that those ones are there. These ones are here, right? These ones are here. This one's here. And you might already also be noticing a pattern in where these angles are, right? Where on the triangle they end up. These would be what we call the base angles, right? But maybe there's other patterns to where they go. One pattern you might notice is that all these triangles have a line of symmetry. They are symmetrical. So how could we describe that? Do you remember what symmetry is, right? Maybe again, look it up in your notebook. The idea would be they can be split into two parts that are the same as each other, right? With a line of symmetry, that means they are reflective symmetry, so it's a reflection that we are making, right? And these reflections across that line produce these images, right? So I can see here some pretty useful little patterns. These are things we're predicting are true, but we don't know these things are true, right? We don't know this. We used this to our advantage before, that these seem to be true about isosceles triangles when we did a previous lesson that you might recall. What was this lesson? If you might remember, it was creating an isosceles triangle, right? We just kind of assumed that all isosceles triangles would look like this. So we started, okay, let's make one. Let's make something that will always become an isosceles triangle, right? So what we did was we started with a triangle, or actually more specifically, not just any triangle, right? We kind of made sure it lined up with some other things because we wanted to reflect this triangle. So we built a triangle where one side was along this line of reflection, right? The other side, well, we could choose wherever we wanted, right? You were allowed to put a point somewhere to determine whereabouts that triangle would be. I would put a point somewhere on the line of reflection and a point somewhere else, right? I was allowed to choose where my points on the line of reflection would be so I could change the height of the triangle, right? And then this other one, the third one that's over here, I could move that around to make it wider or whatever, right? I could even move it up here and make it upside down. Now, after I do this, what was the next thing we did? Well, we reflected it, right? We reflected across this line of reflection here, And when we did so, I had to do that by using my rules of reflection to put a new point here, right? Now these ones were on the line of reflection, so they didn't get reflected. When we did this, all the things that were on the left are reflected onto the right, including those side lengths, right? Like an isosceles triangle. But we also, if reflecting it, we could say that these two things are congruent, right? Because they're the same side length, this point to this point. So that meant that this line of reflection was also a perpendicular bisector, right? And likewise, if this angle was this, then it's also that on the other side. So it's an angle bisector as well. You might remember when we went over symmetry that lines of reflections on corners make angle bisectors and on sides make perpendicular bisectors, right? So if we are using a line of reflection to make an isosceles triangle, we have a lot of awesome information here, right? We know lots of things. We even know that this angle over here is reflected, so it's the same as this angle over here. A lot of the things that we noticed and predicted were true for isosceles triangles, we know to be true if we use reflection to make the isosceles triangle, right? We would know the base angles are congruent. We know that not just those two sides are equal in side length, but also that the bottom can be split into two equal parts, right? Which is the reflection idea. And likewise, this angle can be split. The problem is I don't know all these things are all true for all isosceles triangles. We don't know that all isosceles triangles end up looking like this. The only thing we know about all isosceles triangles is that they have two congruent sides. I don't know that all isosceles triangles are made with a line of reflection. It's true that a line of reflection like that will always make isosceles triangles, but is the other way true? Let's see if we can prove it. If we can prove this, all the postulates, all the conjectures we came up with before become theorems. They become things we know to be true. So how would we prove it? Well, let's start by trying to prove just one of the things we assume to be true, right? So given that I have an isosceles triangle, I'm going to give myself some data to work with here, right? Given that my side length AB is congruent to BC, that's just the definition of an isosceles triangle, right? I would like to prove that the base angles are congruent. So I want to prove angle A, this one, is congruent to angle C, this one, right? Now, this is where it's going to get tricky because in order to prove this, well, normally you might, think, okay, I'm trying to prove angles are congruent, right? What would be the normal way we would do that? Maybe pause the video and consider, how do we normally find angles to be congruent to each other? Okay, so maybe you pause the video, maybe you checked your notes, right? But normally we would use, and again, whenever you hear finding angles are congruent, you should usually be thinking angle relationships, right? But the problem is most of our angle relationships either involve things like vertical angles or linear pairs, yes, or they involve things like, well, two triangles, like corresponding triangles, CPCTC, stuff like that, or like triangle congruence postulates. We don't have any of those here, right? We only got one triangle. If I only have one triangle in this picture, what could I do to make it into two triangles that we can use? How do I make this into two triangles? So maybe pause the video and consider how you're going to make it into two triangles. All right, hopefully you thought about it. How are we making this into two triangles? And the answer is what we'd call an auxiliary line. That is a useful line we add during the course of a proof. Okay, wait. Well, why are we adding a line? Well, think about it. We've already seen a version of this that has two triangles. That's just the version that is split down the middle, right? In this version, we already have two triangles, right? Very convenient. This is right there. So now with two triangles in the picture, okay, we need to figure out what to do. Well, really the first step actually is how am I splitting this triangle? To do this, I'm adding a new point on the bottom. I'm going to call this point D, right? What are we assuming is true? Because when we say split something in half, remember there's two kinds of bisector, right? Are we using an angle bisector or a perpendicular bisector? So I'm going to use a perpendicular bisector, but I invite you to try doing it with an angle bisector, right? Both of them will work, and both of them will be useful in different ways. But we're going to go with the perpendicular bisector for reasons you'll discover. So with a perpendicular bisector, perpendicular means 90-degree angles, right? And bisector means it's splitting the bottom, the side, right, into two equal parts. The angle bisector would be splitting angle B into two equal parts, right? So with this one, I'm giving myself an angle to work with, and I'm giving myself side lengths to work with. So I'm giving myself a little more ammunition, right? Now, Remember, our goal to add a line here was to be able to prove that now we have two triangles, so we can use a triangle congruence postulate, right? One of the things that we use to show triangles are congruent to each other. And there's a lot of different ones we can use here. You can use a bunch, right? So let's remember all the triangle congruence postulates we traditionally use. A lot of people like using the bonus one that we had only in the notes. Don't worry about that one, HL, right? You don't need to use that one. Don't worry about it. You can use it in this one, but you don't need to. So those are the four triangle congruence postulates. Of those four, which one do you think is probably the most useful to use, right? Which one would you go for here? So maybe you thought about it, maybe you paused the video and came back, right? Try doing it yourself, see if you can figure out which one. I think a lot of them are going to be useful, right? Now, angle side angle and angle side, those ones are a little tricky, right? Because we don't know more than just the 90-degree angle, right? That's the only one we got, unfortunately. So probably not using these two, right? But I do have an angle that was now given to me, like 90 degrees, right? And I have two sides. This side of the middle, remember, a shared side is congruent to itself, right? So I don't need congruency markings there to tell me that both of these triangles, ADB and CDB, see how they share the side DB? Are things congruent to themselves? Yeah, right? DB is DB. So we know they share one side, right? One of their sides has equal side length. What about another one? Well, we got the 90 degrees, so we can go BD, then the angle D, right? Or rather angle BDC and BDA, and then DC and DA. So that would be side angle side, right? And I can label that. We got side, angle, and side. But we also have a third side, right? Right here. So we could do either of these two. Side angle side and side both work. See what I meant by giving us lots of ammunition to work with? So we've proven that these two triangles are congruent. If we've proven these two triangles are congruent, then I can say that by CPCTC, right, corresponding parts of congruent triangles are congruent. That means angle A is congruent to angle C. We've shown that any isosceles triangle I make produces two triangles by splitting it down the middle, right, and that the base angles of those triangles are congruent. So all isosceles triangles have this true. But there's actually a lot more we've proven by that, because we've proven they all have reflections, right? They're all symmetrical. And that means we can go a lot of different directions with this theorem. So we can actually rewrite this into a much more useful form for geometry. Specifically, we have two forms for this one. We know that if a triangle has two congruent sides, then the angles opposite of those sides are congruent, right? And we just proved that. But we also know that if a triangle has two congruent angles, then the sides opposite of the angles are congruent. We didn't prove that one, but I invite you to try it. Could you start with not being given that the two side lengths are congruent, but being given that the two angles are congruent, and use the same method, or maybe a different method, to try to prove that you can make two congruent triangles out of the one by splitting it with either a perpendicular bisector or an angle bisector. I invite you to try that out on your own time and see if you can figure it out. But what we've found now is that there's two different theorems that we can use now using the isosceles triangle theorem. If I see any triangle with two congruent sides, it's got two congruent angles opposite of those sides, right? On the other way. And likewise, if I have two congruent angles, the sides opposite of those angles are also congruent. Pretty useful. In the next video, we're going to go over a practice problem set that uses this to do a variety of different problems, showing you how it's useful. But the main thing I want to emphasize before we jump into that is that this is our first big way to find side lengths are congruent, right? We don't have a lot of other ways to do that. So now when you see show two sides are congruent, you're probably going to use the isosceles triangle theorem if you have two congruent angles, right? You might need to do something else, but it's very likely you're looking for this, okay? So I look forward to seeing you in the next video. We'll go over the isosceles triangle theorem practice problems. See you then.